Hello, this is the last lecture in the series for Nanofabrication Technology, and this is lecture 10. In lecture 9, we talk about fabrication of thin film in theory as well as vapor phase deposition. Okay, and the technique that we mentioned in lecture 9 includes evaporation, MBE, and sputtering, and just like in this slide. So this lecture we will cover the rest of the vapor phase deposition, including the chemical vapor deposition, and we will move on to liquid phase deposition to conclude the lecture series. In chemical vapor deposition, basically we want to get reaction of vapor, and the result for the reaction is supposed to be solid, and that solid would be deposited on the substrate into the thin film that we want. So there are so many types of reaction that we can employ. For instance, we can use pyrolysis, basically a decomposition of precursor. For instance, if we have silane, it's silicon hydride, and if you heat it up, it would undergo decomposition into silicon and hydrogen according to this reaction. So silicons formed by this reaction will be deposited as a silicon film, and we need to control reaction rate in the same manner as what we did earlier for nanoparticle synthesis. And in this case, you should notice that the precursor or the reactant of this reaction is vapor, so we can convey this vapor to the substrate easily, relatively easily. And you should notice that on the right hand side of the reaction, this side of the reaction, only silicon is the product of choice. This is what we choose to deposit on the substrate. The rest is supposed to be gas, so that we do not have any impurities deposit as well. Okay, and it would be easier to remove this byproduct from the system. All right. Another thing that you need to consider is that this reaction takes place at 650 degrees Celsius. Okay, so how can we control the reaction to take place only on the substrate, not in the vapor above the substrate? So if you somehow put the substrate into an oven and you set the oven at 650, as soon as these reactants enter the oven, this reaction occurs, right? So that means you will have silicon nuclei form in vapor. This is not what we want. We want silicon nuclei forms on the substrate. So it would be easier if we control the temperature of the substrate to be 650 by heating the substrate only, and the vapor above the substrate is supposed to have temperature lower than this initiation temperature, so that we can control the reaction to take place only on the substrate. Alright, so this is the concept. Of course, there will be a modification that you can try and then you can control. Alright, there's so many ways or so many reactions that we can use. For instance, the reduction, we can use silicon chloride and react with hydrogen at 1200 to get silicon. You can get oxidation, like silicon hydride with oxygen to get silicon dioxide. You should notice that temperature and condition would change with respect to the reaction that we use. We can form compound. We can use also disproportionation reaction, just like this reaction. So basically, I just want to say that there's so many types of reaction, but it would be more convenient if the right hand side of the reaction, the product, only one product is a solid. Okay? And different precursors can be used for deposition of same materials. For instance, if you want to deposit silicon dioxide onto the substrate, you can choose to have silicon hydride as a precursor, react with oxygen. You can also choose the reagent. Instead of using oxygen, you can use nitrous oxide like this to react with the same precursor to get the same product that you want. But of course, byproduct would be a little bit different. Okay? Which one should we use? Which one should you use? Depends on the condition and depends on the properties of the product that you want. For instance, if you want to grow multi-layer of products and one layer is silicon dioxide, okay, you should use the reaction that have the condition that is not so significantly different than the position of other material in your system, so that you don't have to heat it up and cool it down frequently. All right. On the other hand, you can use the same precursor to deposit something different. For instance, if you use silicon chloride, just like this reaction, you may get silicon dioxide on one condition, you may get silicon nitride on the other condition, depending on the temperature. That would be convenient if you want to deposit silicon dioxide layer and silicon nitride layer as the alternating layer. So in that case, you can use one set of precursor and you just swing or you just change the growth temperature, and then the result will be alternating layer of these two materials. All right. The CVD process involves both homogeneous nucleation and heterogeneous nucleation, as I mentioned. In homogeneous phase, if you allow the reaction condition to if you allow reaction to take place in vapor, of course there will be homogeneous reaction. Homogeneous nucleation takes place in gas. And what we want actually is reaction on the surface only. So in order to get good quality of film, you want to somehow deviate this route toward this heterogeneous reaction as much as possible and in the controlled manner. Because if we have homogeneous reaction as a dominating reaction, then you get homogeneous nucleation, or you get particles in vapor, and those particles would eventually drop down onto the surface, making your surface making the impurities on the surface, and the quality of the film would be poor. Okay. Of course, we learned from lecture 9 that heterogeneous nucleation is easier than homogeneous nucleation, but it doesn't mean that there will be no homogeneous nucleation. So you still have to keep in mind how to avoid homogeneous nucleation. And one factor that causes the homogeneous nucleation to dominate will be concentration of reactants in gas stream. The higher the concentration, the higher chance for homogeneous nucleation. Okay. Also, the temperature. The way to avoid homogeneous nucleation is to heat up the surface of your substrate only. You can also adjust type of precursor. The examples I gave you is silicon chloride, silicon hydride. Those are inorganic materials, and the reaction temperature associated with those precursors is usually relatively high. But if you change the precursor to metal organic compound like metal oxide or organometallic compound, those kind of materials should have much lower decomposition temperature or reaction temperature. In that case, you can adjust the reaction temperature down so that you can avoid something else. There's several things that is associated with temperature. First, if you lower the temperature, first thing is you can get the product film that might be metastable phase, the phase that is not stable at high temperature. In that case, you need to avoid high temperature. Okay, or if you want to grow, let's say, amorphous film, in that case, as we learned from last lecture, when we want amorphous film, we want temperature to be low, right? In that case, the lower the temperature, the higher the chance for the film to be amorphous. Either way, this technique, if you change the precursor from conventional inorganic precursor to metal organic compound, this is the technique called MOCVD. So once you change the precursor, the whole chemistry associated with it will be changed, and therefore all the parameters that you need to control will be changed as well. The good thing is this kind of technique makes the reaction relatively easy to take place. Okay. The other way to make the reaction a little bit easier is to use plasma. In that case, the reaction will be called PECVD, or plasma enhanced CVD. Plasma is basically radicals in gas phase, so that once you get radicals attacking the precursor, chemistry will be totally shifted, totally changed. And whenever you have plasma enhanced, the reaction can be conducted at relatively low temperature. Both techniques give you high deposition rate, and as I said, the temperature of the film deposition can be lower, relatively lower. Okay, and there's a special circumstance for CVD called atomic layer deposition, or ALD, and in this case we call this technique to be self-limiting growth. This is different than CVD. In conventional CVD, if you let the reaction run, if you have continuous feed of the precursor to the system, the film would grow continuously. So in order to control the thickness of the film, you have to control the time that your substrate is exposed to the precursor. Okay, and that is not quite easy to do. So the thickness of the film in CVD cannot precisely control. On the other hand, this technique was designed to control the thickness to precise number, because the concept of this technique is self-limiting growth. So it's grow one layer, atomic layer, at a time. So if you want some certain thickness, you can calculate how many times of deposition you need. Okay. So as I said, the film would be precisely controlled to the thickness that you want, as well as the control of the smoothness of the film. The thickness can be as small as angstrom. Okay. The concept of this ALD is like this cartoon. Suppose you have a substrate, you have to modify the substrate with some chemical function. Okay. And I will show you the examples later on, but the concept of this is basically add some functional groups onto the substrate by surface modification. Okay, suppose you have this green function, and then once the whole substrate is covered by this function, there will be no more reaction taking place, because this molecule does not react with this function anymore. Okay, so that should limit the coverage of the film to be just one atomic layer. So once you cover the first layer, then you change the precursor to something else. For instance, this reactant A, which has these groups matching the functional groups on the surface. So if you have a match like this, as long as you supply this reactant A, there will be reaction all over the place until the whole surface is covered by reactant A. Then this group on the top of this layer is no longer compatible with the functional groups of reactant A, so therefore there will be no more reaction taking place once this red layer is formed. Okay. So we form one layer of A, no more coating after the whole surface is covered. Then we can change to another reactant. So if this reactant B has this function, this group compatible to this function on the surface, then you can have the reaction form, and reaction will continue until the whole surface will be covered. That will be another layer of reactant B. And you should notice that once layer of B is formed, this function would be very similar to the green layer. So therefore, if you change the precursor to A again, you can form another layer of A, and then you can do the alternate sequence of A, B, like that. That would give you the growth of the foam. Okay, this is the concept of atomic layer deposition. As an example, if I have silicon substrate and I supply water or steam, water vapor, there will be reaction between hydroxyl group from water with silicon on the surface to form silanol functional groups or OH groups here. This first step is the green step, is the surface modification of the substrate. Okay, so the main purpose here is to grow hydroxyl group. Then I can switch from water into titanium tetrachloride. There will be reaction between hydrogen here and chlorine here to form hydrochloric acid, and then titanium and oxygen will be bound together to form titanium oxygen bond. So everywhere that we have hydroxyl groups, as long as you supply titanium tetrachloride, there will be reaction like so. Okay, once the whole surface is covered by this titanium chloride group, it's just like the red layer here. There will be no more reaction, because as doesn't matter whether you keep supplying titanium tetrachloride, that will not react with this chlorine. Alright, so then you can change titanium tetrachloride to water. That would be our reagent or reaction B. Okay, once you have water, hydrogen here and chlorine here would form hydrochloric, and eventually the chloride groups will be replaced by hydroxyl groups. So everywhere that you have chlorine, as long as you keep supplying hydrogen water, you get the chlorine replaced by hydroxyl groups. Okay, so of course you need to purge hydrochloric acid out from the system continuously, so that you can form hydroxyl groups on all of the arms of this titanium. And then there will be the second steps of the reaction, that this one proton from one side of this oxygen and the other hydroxyl groups would condense to form water, and titanium would be bound together by oxygen bridge. Okay, so as long as you condense this water out, you form oxygen bridge, and eventually you get titanium oxygen titanium bonding like this. After that, if you change the precursor back from water to titanium tetrachloride, everywhere that we have hydroxyl groups, just like when we modify the surface, will be replaced by chlorine, titanium chloride groups, like so. So if you keep changing the precursor from A to B and back to A to B again in cycles, eventually you will form titanium dioxide layer. Okay, so this is titanium dioxide network. Of course, the structure of the titanium dioxide crystal will be totally different than in this cartoon, but the concept will be like this. So that means the thickness of this titanium dioxide film can be controlled by how many cycles that you change from titanium tetrachloride to water. Okay, this picture shows you the growth of titanium dioxide film in this area, the light area here, by using 40 cycles of AB. A is titanium tetrachloride, B would be water. Okay, and you see that at this condition, one cycle should give you 0.43 angstrom, precisely 0.43 angstrom. So if you know that you want 17 angstrom thick of this layer, you can calculate back to 40 cycles. Okay, so that's how we control the thickness by this technique. One thing about this technique is that you will see from this picture that the coverage is quite uniform. So the thickness will be totally uniform all the way, everywhere in the system, and the substrate is not limited to flat plate. You can cover foam on particles, spherical particles as well. Okay. The type of material suitable for this technique includes oxide, nitride, fluoride, or even elementals. Okay. The good thing about the technique is precise control of thickness down to the angstrom level. You can control it by controlling the cycle number. Alright, and it has conformal coverage. That means if you have pores inside your substrate, like in this picture, if you use conventional evaporation technique or PVD, deposit foam, the foam, according to the mean free path as we discussed in lecture 9, the foam would be formed only on the projected area, the projected line that the growth species lands onto the surface. On the other hand, for ALD, since the reagent is in vapor phase, that vapor would go into these pores and cover everywhere inside the pores. So the reaction would form everywhere inside. This is called conformal coverage. Okay, so this is one of the unique advantage of this technique. Just like in this picture, this bright line is the layer formed by ALD. You can see that even though the scale is nanometers, the width of this trench is really small. If you use other techniques, you might not get the penetration of the precursor down to this deep trench, but ALD you can. Okay. The other thing that you should notice is that the thickness of the foam is quite uniform all the way, totally uniform. Okay, so this is a good advantage of ALD. But the bad thing, of course, everything has disadvantage. Disadvantage of ALD is that it takes really long time. One deposition rate takes maybe it has low deposition rate. Per cycle is in angstrom level. Okay, so if you want to grow thick layer, you have to wait forever. So this technique is not quite suitable, or not quite a proper technique for growing thick foam. So we have discussed all techniques about vapor deposition. So it's time for liquid phase deposition. In liquid phase, everything would be the same. Basically, you create growth species in liquid, and then the growth species migrates from bulk liquid to the surface of your substrate, just in the same manner as PVD. But the reaction involve liquid usually takes place as lower condition. Okay, so the good thing about liquid phase deposition is that the condition is not as severe as in gas. So whenever you want the foam of sensitive material like organic, inorganic hybrid material, this technique would be suitable. And since the temperature would be lower, much lower, sometimes liquid phase deposition can be done at room temperature. So the foam should have lower stress. Why did I say that? So think about this. If you grow the foam at high temperature under maybe CVD, the foam may be formed at high temperatures, 400, 600 degrees Celsius. When you cool it down to room temperature, there will be the shrinkage of the foam, right? That would cause the stress in the foam. That stress would be the residual stress in the film caused by the cooling from the reaction state down to room temperature. But if you can grow the film at room temperature, there's no cooling involved, so your film should not have the stress inside. Okay. There are several techniques that we will discuss in this lecture, including sol gel foam, electrochemical deposition, Langmuir blotted foam, and self-assembly monolayer. Okay. For electrochemical deposition, this is what you learn in high school. This is called plating, so we will not discuss this in the detail. For sol gel foam, it's just the same chemistry as sol gel that we discussed in lecture 6. Okay, during that time we use sol gel to fabricate nanoparticles. In short, we have precursor, then you react precursor to form nanoparticles called sol, right? And then these sol would form the three-dimensional structure called gel, and that gel would form into particles eventually. So if you have sol suspended in liquid, then you transfer that sol onto the substrate. The gelation would occur on top of your substrate, and then eventually you form the materials on the substrate. So the key features of this sol gel foam in this case is how to form the foam on the substrate. Okay, the chemistry will be exactly the same as we discussed earlier in lecture 6, so I'm not going to repeat it again. So in this case, we just focus on how we can form the foam of sol onto the substrate. There are several ways that you can consider. Spin coating, like this. Suppose you have the substrate, you put onto the rotating platform, you rotate it, and you put the sol as a droplet inside, and then by centrifugal motion the liquid will be dispersed as a thin film on this substrate. Of course, the thickness of the foam can be controlled by the rotation speed, okay, and the uniformity of the foam also is controlled by the rotation speed. You can use dip coating, just like in this picture. You have substrate dip into the sol, okay, sol mixture. Once you pull this substrate up, by surface tension, liquid would be form thin layer on this substrate. Of course, if you pull this substrate quickly, there will be nothing formed onto the surface because the surface tension would pull everything downward. Alright, but if you pull this substrate up slowly and let the solvent evaporate from the foam, there will be thin film formed on this substrate slowly. Okay, so in this technique for dip coating, one thing that you need to consider is the speed that you pull this substrate upward, and that speed must be slow enough to balance with the evaporation of this solvent. Okay, if you pull it too fast, there will be no foam or really thin foam form onto the surface. If you pull the substrate too slow, then the foam will be quite thick. The thickness of the foam can be controlled by the speed of pulling. Okay, and during the evaporation, when we consider gel, okay, the gel is solid encapsulated in liquid. So whenever you have evaporation, the gelation will be accelerated. So not only you have to consider drying of the gel here, that would be associated with the foam thickness, you need to consider chemistry as well, because if you drive the solvent out, for instance, if the solvent is water, when you drive the solvent out, the chemistry of hydrolysis and condensation will be affected if the reaction is not completely done yet. Okay, so when you do the dip coating of sol gel foam, you need to balance the speed by keeping the evaporation as well as the chemistry in mind. The third technique would be spray coating. The spray coating is just like when you use a spray can, okay, a can of spray paint to paint on something, but instead of using paint, you're just using sol in the same thing, just like aerosol technique that we discussed in previous lecture. The point is, once you form the foam by either technique, gelation, condensation of the gel, and solidification by removal of the solvent takes place, sometimes together, sometimes consecutively, okay, depending on the chemistry of your reagent. So you need to be aware that these things can take place at the same time, and that would affect the quality of your foam, not only affecting the foam thickness, but it will affect, let's say, the crystal structure of your product as well. But sometimes when you have evaporation with if you have fast evaporation from the gel, the foam tends to shrink, okay. When you have the shrinkage of the foam, you may induce the stress inside the foam that would give you cracks. So too fast of the evaporation may result in cracks in the foam. That's why the drying must be controlled. So it depends on how you dry or how you fabricate the foam. If you dry the foam together with the fabrication, for instance, like from dip coating, you need to control the dipping speed. If you coat it first by, let's say, spin coating, and you dry it later, then you have to control drying condition so that you can avoid too fast evaporation, okay. The foam by this sol gel foam is usually porous and amorphous, but it's not limited to amorphous foam. You can grow crystalline foam, polycrystalline foam by sol gel techniques, but it is relatively hard to get single crystal foam by sol gel technique, okay. The another technique that we will learn in this lecture is called Langmuir Blotted foam or LB foam, okay. It relies on the use of surfactant. We discussed about surfactant once before in the lecture about kinetics approach for the formation of nanoparticles, okay. During that time we said that surfactant is a molecule that has two parts. One part is non-polar, hydrophobic non-polar part. The other part would be hydrophilic polar tail head, okay. During that time we said that the hydrophobic does not like water, so if you disperse surfactant molecule in water, there will be a tendency for that molecules to protrude this tail, this hydrophobic tail, up in the air, keeping its hydrophilic head in water, okay. During that time I said that if you add more and more surfactant in water, you eventually get surfactant on the surface like this picture. If the concentration exceeds what we call CMC or critical micellar concentration, you form micelle in the aqueous phase, right? But if the concentration is not reached CMC yet, so you get this surfactant molecule dispersed on the surface like this picture. So if I have a blade like this and I push these surfactant molecules together, you can form somewhat like a dense layer of surfactant foam. So if I have a substrate underneath this water and I pull this substrate up, if my substrate is polar and is in opposite charge with the head of these surfactant molecules, there will be interaction between the head part of your surfactant molecules and my substrate here. So there will be a coating of this substrate, lifting the surfactant out of water. Of course, now if you design these surfactant molecules to be something that you want to coat on the foam, eventually you get this layer as a monolayer on your substrate. This technique is called Langmuir Blotted foam. Okay, so this is a transfer of surfactant molecules onto the surface. It is a result from interaction between these surfactant molecules and substrate. Oh, by the way, sometimes people call these surfactant molecules as amphiphilic molecules. Okay, if the substrate is hydrophilic, just like in this picture, the hydrophilic part of your surfactant would be attracted to my substrate here, just like in this picture. So the foam would be formed when you pull the substrate out of water. On the other hand, if your substrate is hydrophobic, the foam would be formed when you push down the substrate, like in this picture. Okay, in this picture the substrate is hydrophobic. The hydrophobic part would interact with the substrate to form the foam during the pushing of the substrate down. Alright, now if I start with hydrophilic substrate, I form the first layer of surfactant on the substrate, and then now the surface here becomes hydrophobic. If you want to add another layer, then you have to form the layer when you push it down. Okay, so if you're repeating the pushing up, the pulling up, the pushing down like this, you can form the layer that you want. Of course, it depends on the application and type of these surfactant molecules, that what you want to do. If you have surfactant molecules containing metals and maybe long chain of hydrocarbon, once you form this layer and you heat it up, that hydrocarbon part would be burned, and eventually you will end up with metal oxide layer. That's one way to create metal oxide layer on top of the substrate. Of course, you can do something else. If you want to modify the substrate to get organic tail, you may also use this technique as well. Alright, the strength of the interaction between the surfactant molecules and the surface of the substrate is a critical factor in this technique. If the surfactant has strong hydrophilic head, then it would stay in water, because water is also hydrophilic, right? So if you consider water having charge and the polar head of the surfactant has charge, if your head of the surfactant is strongly charged, then it would prefer to stay in water. It will not attach itself onto the substrate. That's not what you want, right? So there will be no foam form if the charge in the polar head of the surfactant is too strong. On the other hand, if the head group of the surfactant is too weak, is not strong enough, then the interaction between the surfactant molecule and the substrate might be too weak to pull it up, and eventually you will not get the foam form as well. So this technique relies on the balance of charge between the head group of the surfactant and the substrate. Alright, the last technique that we will mention in this lecture is called self-assembly. It is basically a reaction in liquid, so that the molecules would arrange on the surface spontaneously in similar manner as ALD, but taking place in liquid. Okay, the good thing about this technique sometimes is called chemical bath deposition. Okay, the good thing is you don't need to purge reactants between cycles, because the byproducts from reactant would be would diffuse into bulk liquid, or the reaction takes place spontaneously by itself. The driving force for self-assembly include the electrostatic force, hydrophilic force, or chemisorption between the chemical reagent and the surface. Okay, these three factors involve how molecules will be transferred from liquid onto the surface and bind itself onto the surface. Okay, the cartoon for this technique looks like this. If you have a molecule that has several functional groups, the head functional groups here supposed to be active to the substrate. Okay, somehow this red group supposed to like to stay on the substrate. You need to consider molecular interaction between this red group and the substrate surface. There are several ways to bind this group to the surface of the substrate. The yellow part is basically RQ chains. Okay, the chain length depends on your application. Sometimes you want long hydrocarbon chain, sometimes you do not want the chain at all, depending on the application. At the end, you need termination functional groups. Okay, if you want multi-layer foam, this termination functional group should allow the reaction of the next layer. But if you want single monolayer of the foam, then this termination group would prevent further growth of the foam. Right? So the molecules that you need to put on the substrate should have the function according to application that you want to use. You may have interchain van der Waals or electrostatic interaction between RQ chain here, so that you have maybe cross-linking between molecules. All right, but it's not necessary. Now, if we go back here, I want to discuss about interaction between these head groups and the substrate. There are several kinds. First, you can form covalent bond. Okay, the most famous bond will be silicon-oxygen bond. Okay, this silicon might come from the molecules that you want to put onto the surface. The molecules containing silicons and hydrocarbon is called organosilane. Okay, this oxygen would be oxygen as part of your substrate. Maybe if you want to grow something on glass, that glass would be silicon dioxide, that oxygen would come from glass. Or you may have some metals, and then you treat that metals to have maybe oxide layer or maybe hydroxide groups on the surface. Okay, so the first step would be treating the surface to have oxygen, and then add organosilane. There will be reaction onto the surface to bind this silane to oxygen onto the surface. Then you form this bond. That link will be formed. Okay, you might have this S metals polar interaction. This S is basically sulfur. Okay, sulfur has strong interaction with noble metals like gold. So if you want to attach molecules containing sulfur like thiol or sulfide on gold, that part of sulfur, that part of the molecules, the sulfur part of the molecules would turn toward the gold and bind to the gold substrate by polar interaction. You may have ionic bonds between absorbed molecules and substrate. You may absorb these molecules onto the substrate first, and then you may absorb these molecules onto the substrate if this substrate is metal or ionic compound. Okay, these molecules contains high polar part of the molecules. Maybe amine has lone pair in amine groups. Alcohol, you have lone pair in oxygen group in alcohol, or even carboxylic acid groups. those electrons will be attracted to protons onto the surface. So if your surface has metals which has a proton, then you can have ionic bond. Okay. Examples for self-assembly techniques would be something like this. Suppose I have substrate and I hydrolyze the substrate so that I form hydroxyl groups first. If I intend to rely on the reaction between silicon and oxygen to form covalent bond, I choose these covalent organosilane materials. R is alkyl group, Si in silane, and X would be halogen. Like this. The halogen part would react with hydroxyl part, just like in the example I showed you in ALD. If this silicon is bound by 3 chlorine atoms, chlorine would react with these hydroxyl groups, okay, to form hydrochloric acid, and then silicon would bind covalently with this oxygen, like this picture. Alkyl group would protrude out from the surface. This function depends on your application. Okay. Now, the termination group in this case, if the end of these alkyl groups allow hydrolysis, then you might form hydroxyl group at the end of this alkyl group. Eventually, if you keep this precursor in the bath, then reaction between this halide and this proton would continue, so that the second layer of these molecules would be formed on top of this first layer. So these cycles would take place continuously as long as you keep this precursor and you keep the termination group to be if the termination groups here allow hydrolysis to take place and you have maybe water inside your system. Okay, so this is called self-assembly. It's basically reaction on the surface but in liquid phase. As I said, the key point would be how you can attach this molecule to the surface. It relies on chemistry. Okay, so in this case, this example, I relies on silicon oxygen reaction, but you can also change. If this substrate is gold, you can change this group, the head group, to be sulfur, and then sulfur would interact with this gold substrate by polar interaction, and then you form something like this as well. Alright. The good thing about self-assembly technique is that it is relatively simple. You can get reaction at room temperature, and you can control the foam. You can get multi-layer foam with functional group that you want, and this can be done layer by layer. Okay, so you may have maybe 2 baths of different precursor. You immerse substrate in first bath to form 1 layer, and then once the first layer is formed, you can immerse into the second bath to initiate the second layer, and then you can go back and forth in the similar manner as ALD. But imagine if you have ALD, you need to purge everything in gas phase out, which is not quite convenient, as it's not as convenient as dipping in 2 beakers. This technique is very famous for the formation of inorganic and organic hybrid foam. As you can see from my examples, if I choose the precursor to have organic chain, that material should have inorganic part and organic part as well. Okay. Then if you design the termination group to terminate reaction after the first layer is done, then you can form monolayer by itself. This technique is called self-assemble monolayer, or SAM. Okay, it will form 1 single layer in atomic level that you don't have to control anything. The chemistry will control it to be monolayer by itself. So this is quite unique technique, but it relies on chemistry quite a lot. You can also form, let's say, the first layer by forming thiol layer onto the surface, and then you can instead of having the second layer of molecules formed on top of first layer, you can dip that film onto the colloidal particles. Okay, for instance, if your termination group is sulfur, and then you dip that film in colloid of gold, that gold particles would attract to sulfur onto the surface. Then you can form what we call nanoparticle layer as a thin film as well. Alright, so for this lecture I gave you several examples for the fabrication of thin film in liquid. Okay, as you can see, the technique basically in this lecture we talk about reaction, the formation of film by means of reaction, but that reaction can take place either in vapor or in liquid, but chemistry is the most important thing in chemical vapor deposition or even in self-assembly thin film. Alright, so for the lecture so far, we have overall of 10 lectures starting from lecture 1 to 10, and first 7 parts would involve the formation of nanoparticles, and then nanorod, and at the end thin film. You need to understand that mostly it involves nucleation, growth, okay, formation of supersaturation or formation of growth species to get supersaturation of growth species, and then nucleation of growth species to form nuclei. Okay, if the nuclei is formed in fluid, it's called homogeneous nucleation, and that would go into the formation of nanoparticles. If the nuclei is formed on the substrate, that would be what we discussed in the film formation. Then the third step will be growth. Okay, the growth of the growth is basically the deliver of growth species from the bulk to the nuclei. Okay, if the growth species lands on the surface uniformly, you end up with nanoparticles. If it lands on some preferential plates or preferential planes on the surface, then your particle will no longer be spherical. It will be anisotropic growth, just like in nanorod. And then if the growth would be on the substrate, then you form the thin film. You see that 0-dimension nanoparticles, 1-dimension nanorod, and 2-dimensional film, the mechanism relies on the same thing. Okay, only the minor details are different. So that's conclude my lecture. Hopefully you get something from this series of lecture. Thank you for watching.